So today we're going to look at another integration technique. I know, another one. And before we jump right into the actual technique, what I'd like to talk about first is kind of some motivation for that particular technique. So in the video lecture where we looked at approximating area, this was like one of the first video lectures that we had for the course, we looked at the area of the unit circle in the first quadrant. And what we did is we used rectangles to approximate the area. Now remember that because of geometry, we know that the exact area, because the area of a circle is pi r squared, the area of the entire circle is pi. Since I'm only looking in the first quadrant, I have a quarter of that. So the exact area under this curve, or the exact area of the unit circle in the first quadrant, is pi over 4. Now if I were to write that out in some of the new, the new notation that we know, the notation that we didn't know when we first did this, is the area would be the integral from, let's take a look, from 0 to 1 underneath our curve. Now remember that the unit circle is x squared plus y squared equals 1. That's based on the Pythagorean theorem. So we can solve for that in the first quadrant. It's square root 1 minus x squared. Okay, so again, we know that this equals pi over 4 based on using geometry. But let's say for a second that we didn't know that the area of a circle was pi r squared. That's actually something that people didn't always know about. So we're going to see if we can maybe, instead of using geometry, if we can use some integration techniques to evaluate this definite integral. And again, this definite integral represents the area of the unit circle in the first quadrant. Okay, so I'd like us to just think about what some of the techniques are that we currently have. So you might be asking yourself, well, do I just know the antiderivative of square root 1 minus x squared? Okay, and the answer to that would be no. So antiderivative known. This should be kind of the list of steps that you go through when you're trying to integrate something. Your first thing you should check is, do I just know the antiderivative automatically? In this case, no, but it might look kind of familiar to an antiderivative that we do know. I do know that the integral of 1 over root 1 minus x squared, I do know that that is arcsine. Well, that's a good thing to know, but it's not really helpful in this case because I don't have 1 over. I just have the square root of 1 minus x squared. So this is not going to work. Okay. Maybe your second thing you should ask is, can I use u substitution? That is, will u substitution work? Well, let's see. In general, when we use u substitution, we usually make the inside thing, which in this case would be the 1 minus x squared. We would usually make that u. And let's see, if I did that, I'd have du, the derivative of u with respect to x, is negative 2x. So du is negative 2x dx. Now, this negative 2, remember, we can take care of that if we need to. We could say negative 1/2 du equals x dx. Again, because we don't have a negative 2 up here, I can take care of that this way. But notice that we have an x dx here, and we do not have an x dx up here. So if the integral had been x root 1 minus x squared, absolutely I could use u substitution. But again, you know, we don't have that. We don't have an x here. So this technique also is not going to work. You probably kind of see where this is going. In addition, if we tried integration by parts, that also wouldn't work. Feel free to attempt it if you want to. It just gets pretty nasty looking. So none of the techniques that we've learned so far are actually going to help us to evaluate this integral. Okay, so we're going to learn a new technique. I know. And this technique is called trig substitution. Or if I want to be nice and mathematical, trigonometric substitution. So we do have a substitution idea, but it's a little different from my u substitution where I make u equal to something that I see in the integral. In this case, instead of using a u, I'm going to make x some trig function. I'm just going to write that for right now. Now, you might be wondering why we would do that. Well, one of the reasons why it'd be nice to actually bring trig into the situation Well, it's not so far off because I'm talking about the unit circle right now. It makes sense that trig might come up in, in there somewhere. But also, we have all these trig identities that can sometimes help us to simplify things. So here is kind of a list of helpful trig identities. Some of them we might use as we go through this particular section. Some of them we might not. But here's a bunch of them, and they may or may not become helpful as we go through. Now let's take a look at our integral again here. I have square root of 1 minus x squared. So it'd be nice if I could somehow match this with one of my trig functions. And you might be wondering, how can I match it? Like, I don't even see any trig in this original thing. Well, notice I have 1 minus something squared. Okay, let's just think about that. 1 minus something squared. I want to take a look here at my identities. Okay, so notice here I have something squared plus 1, something squared minus 1, but these two are kind of similar to this. I have 1 minus something squared. In this case, it's a sine squared. In this case, it's a cosine squared. And so I'm going to use one of these, and I'm going to use this one right here. And the reason I'm going to do that is because of the fact that I could use either one of these, but conventionally we use this one. And notice that if I were to make x sine theta, then 1 minus x squared would be 1 minus theta, sine theta squared. So let's take that a little bit further. So we're going to use this one right here, and I'll go ahead and write it here. Again, I know that cosine squared is 1 minus sine squared. So what I'm going to do is I'm going to let x equal sine theta. So if I do that, let's jump back down here. I'm going to go ahead and write this as an indefinite integral just for the time being, because I don't want us to worry about the bounds for right now, but we will fill that part back in later. So here's my integral. Now notice if I make x sine theta, then I have square root 1 minus x squared. Now x squared is the same thing as sine squared, right? Just squaring both things. So this is the same thing as 1 minus sine squared theta. Okay, hopefully you feel comfortable with that replacement. Again, I'm just saying I'm going to let x be sine theta. So if I replace this with sine theta, I get 1 minus sine squared. Now notice that we can eventually do this, and I also have a square root, which is going to be kind of nice. But we need one other thing here. I have a dx, and just like I replaced the x, I need to also replace the dx. So let's see how we can go about doing that. This will look very familiar because it's very similar to what we do in the u substitution. If I let x equal sine theta, well, I can take the derivative of both sides with respect to theta. Oops, d theta. Okay, so I'm taking the derivative of both sides, and I'm doing it with respect to theta because I'm taking the sine of theta. So it's like theta is my input and x is my output. So if I do that, over here I get dx d theta, and over here I get the derivative of sine, which is cosine. And again, similar to u sub, I can think about multiplying both sides by this d theta, so I can solve for dx. So I get dx equals cosine theta d theta. Now let me actually go ahead and I'm going to take this a step down here instead and write just what I wrote before, root 1 minus sine squared. Okay, now again dx, I'm replacing this piece. Dx is cosine theta d theta. Just a direct replacement, right? And I didn't choose this to be my dx, right? That came from the fact that I chose x to be sine theta. This was a choice. This was a result of that choice, okay? So notice the new integral that I have here. I have now the integral of root 1 minus sine squared theta times cosine theta d theta. Now, this doesn't necessarily look that much better than what we started out with, but it does kind of involve things that we're more familiar with integrating. So to make it even more so, I'm going to go ahead and use a trig identity. I haven't really used any trig identities yet. All I've done is set x equal to sine theta. I'm going to use a trig identity. I know that 1 minus sine squared theta is equal to cosine squared theta. So I have square root cosine squared times cosine. So now I have root cosine squared theta times cosine theta d theta. Now, of course, I have a square root and a square, so those undo one another, giving me cosine theta, and I have another cosine theta d theta. And when I multiply these two together, I get the integral of cosine squared. Okay, so let's just think about the steps that we just took here. So, I let x equal sine theta, and that allowed me to rewrite this integral in terms of cosine squared. That actually is slightly more convenient for us. I'm going to be able to integrate cosine squared using a technique, whereas up here didn't have a lot of options just from that beginning point. So the way I'm going to integrate cosine squared, now notice that this is a composition. Now if I had a times sign here, I could just use u substitution, right? Because then I'd see an inside function and its derivative. That's not the case here, so instead I'm going to look back over here at my helpful trig identities and see if we can come up with one that's going to help us to integrate, in this case, cosine squared. So let's take a look. Well, let's see. I have a cosine squared is 1 minus sine squared. That's not really going to help me because I still would have to integrate sine squared, which is basically the same amount of work as integrating cosine squared. I'm looking through the rest of these. How about, I wonder if this one might help. Cosine squared is the same thing as 1/2 times 1 plus cosine 2 theta. Now you may or may not be familiar with this trig identity. If you're not, that's okay, because we can always look these up, right? And the point here is finding which ones are useful for us. So in this case, it looks like this one's going to help us out. So again, I have cosine squared. I'm still integrating. I haven't integrated yet. 1/2 1 plus cosine 2 theta. And again, d theta. So I just used this trig identity. This one. So cosine squared is 1/2 1 plus cosine 2 theta. Now you might be wondering if that's better than what I started out with, and the answer would be yes, because I know how to integrate cosine of 2 theta, right? That is going to be kind of a straightforward u substitution. So actually going into that, let's do a little bit of side work in case we're not quite comfortable yet in integrating. This part's easy, right? Integral of 1, that's easy. Let's just look at this piece separately for 1 second here. So if I was to integrate this, like I said already, I would use u substitution, where I'm going to make this u. Again, I'm doing that u sub here because I have an inside part. So u is going to be 2 theta. Derivative of both sides. Derivative of u is going to be 2 d theta. Derivative of 2 theta would be 2. So I get du over d theta equals 2. Multiply both sides. I don't have a 2 here, so I'm going to do 1/2. Okay, so that replaces my u, and now d theta is 1/2 du. And if you need to pause the video to catch up on things, I know I'm moving somewhat fast here, but if you're kind of not sure about what's going on here, feel free to pause the video and kind of maybe even just try it on your own to get familiar with it. So what I have then is the integral of, so this would be cosine of u, now 1/2, so I'll pull the 1/2 out in front, du. So I get 1/2 integral of cosine of u is sine of u. I'll tag on my plus c right now. And then I can put what u was back in there. So I get 1/2 sine of 2 theta plus c. Now you might just automatically know that when you integrate something, so I could have not done this. Another thing you can always remember is that when you integrate this, it's going to be the integral of cosine, and then with this piece back in there, and then divided by whatever this coefficient is. So for example, if I was integrating cosine of 4 theta d theta, that would be 1/4 sine 4 theta. So this is something that you can just go ahead and remember. It can be a little bit of a time saver. Similarly, if I was integrating sine of 7 theta d theta, that would be, well, I'd have 1/7. The integral of sine is negative cosine. So if you want to remember that, that could be, again, a good time saver. But you can always go back to u substitution if you aren't quite comfortable with that. So let's see where that took us. Again, I have 1/2, and now I'm going to integrate. Okay, so I know all of that work up here in order to get to something like this, which will now allow me to actually find the antiderivative. So I get, this is my constant, you could pull that in front if you wanted. The integral of 1, now be a little careful here, we're so used to dx's. The integral of 1 here would not be x, the integral of 1 would be theta, since I'm integrating with respect to theta. So I get theta, and then I just evaluated this, 1/2 sine 2 theta. And because I'm writing this as an indefinite integral, I'm going to go ahead and use my plus c here to make it a more general antiderivative. Okay, now, we can somewhat rejoice because we have found the antiderivative, but there's one little problem, and that is right now my antiderivative is in terms of thetas and not in terms of x's, right? So depending on what we want, if we wanted to find the general antiderivative, what I could do is I could plug basically figure out what theta is from this initial equation that I had. But I'm also noticing that my initial thing that I wanted was the integral from 0 to 1. So it was a definite integral that I was interested in. So let's go ahead and we'll do this two different ways. Okay, the first way is we'll look at this as a definite integral. So let's start off with that. So again, what we did is we went from 0 to 1, square root 1 minus x squared, and we were able to write that as 1/2 theta, 1/2 sine, that's weird too, 2 theta. And I'm not going to worry about my plus c because I'm using a definite integral and I now want to evaluate. So I'm going to put my evaluate bar here. But here's the thing, this is not going to be from 0 to 1, right? X equals sine theta. That was my original choice. X is ranging from 0 to 1. Yes? Okay, so if x is ranging from 0 to 1, my question is, what is the range for theta? Because notice my integral here is in terms of theta. So I need to adjust the bounds so they are, again, in terms of theta. Here they're in terms of x. Here I want them to be in terms of my new variable theta. So let's think about this. If x equals sine theta, then and my x values are ranging from 0 to 1. Okay, so let's think about the unit circle here. And we could even talk more specifically about the first quadrant because this is saying the sine of my angle is ranging, and remember the sine gives the y coordinate, so it's ranging from 0 to 1. Now I can think about what angles are spanned to go from a y coordinate of 0 to a y coordinate of 1. Now notice it's going to be all the angles between an angle of 0 and an angle of, well, this angle is pi over 2. Okay? So again, if sine is ranging from 0 to 1, then I can say my theta, my angle, is ranging from 0 up to pi over 2. So that's my new bounds, 0 to pi over 2. Now the nice thing about doing it this way is I don't have to bring my x back in, and I can still evaluate the definite integral. So let's go ahead and do that. So I have 1/2, again, theta is ranging from 0 to pi over 2, so I'm using the fundamental theorem of calculus. I'll pull the pi over 2 in. 1/2 sine of 2 pi over 2, minus, plugging in the 0, 0 minus 1/2 sine of 2 times 0, and need one more, and let's see what we get. 1/2 pi over 2. Let's see, this would be sine of pi. Pi is over here. It has an angle, or sorry, a sine, a y coordinate of 0, minus 0 minus sine of 0, which is also 0. So basically all the stuff over here gets wiped out, leaving me with 1/2 times pi over 2. And there's that pi over 4 value that I was looking for. Again, that matches with what we initially thought using geometry. The area of the unit circle in the first quadrant is pi over 4. Okay, so if all we were asking was just this, that would be our answer, and we could call it a day. But let's just say for the sake of practice that I also wanted the indefinite integral. So if I wanted the indefinite integral, then basically what I would need to do is, here's my integral. I again did all this work to get to here, plus c, right, indefinite. So I need to write this in terms of x instead of writing it in terms of theta. I want my integral is in terms of x, my antiderivative should also be in terms of x. So again, what I'm going to think about is the fact that I originally said that x equals sine theta. That's my relationship between theta and x. So it's actually pretty straightforward to now solve for theta. If x equals sine theta, then theta is going to be the inverse of sine or arc sine. Now you could write it this way, or you could write it this way. Either one of those. I'm usually like this one a little bit more. So technically, here I'm going to give two answers. Technically, I could go ahead and rewrite this as 1/2. Now again, theta is arc sine x. So I'm going to replace this one. 1/2 sine of 2 theta is arc sine of x. Now technically I could write the antiderivative as this. Okay, but we generally don't like to write things like this, sine of arc sine. There's usually some simplification that we can do, and we talked about this when we looked at derivatives of inverse trig functions initially. I know that seems like a long time ago. But we're going to go ahead and we're going to try to rewrite this. We can't really rewrite this one, but we can maybe simplify this one a little bit so that we have a slightly nicer answer in the end. So here's how we're going to do that. Okay, so let me just jump back up here to where we had started. Now the first thing we're actually going to do is we're going to use, I know, another trig identity. Because it's hard for me to kind of think about this double angle. It'd be easier if I had it in terms of just theta. So here's another trig identity that's somewhat helpful. Again, I have a sine of 2 theta here, and sine of 2 theta is 2 sine theta cosine theta. So let's go ahead and rewrite it as that. So I have 1/2, and again, sine 2 theta is 2 sine theta cosine theta. Now again, it's okay if you don't have these, completely memorized. It's more about knowing when to use it and how to use it. So let's see where that takes us. The 2's I'm seeing cancel, so I get sine theta cosine theta. Okay, now again, I could technically put arc sine x in here and arc sine x in here. But that's not any better than what we had up here. So what we're going to do is we're going to rewrite this in terms of basically what we have here. So again, I know that x equals the sine of theta. So if we think about that on a triangle, now again, trig, right triangle. Now it is important that you do remember your SOHCAHTOA here. Okay, so if I'm going to go ahead and say that this is my angle theta, okay, x equals sine theta, theta is my angle, I'm going to call this angle here theta. So that means that in terms of SOHCAHTOA, my sine of the angle is going to be the opposite side over the hypotenuse. Now notice that I do know that sine of theta is x. And because we're on the unit circle, I'm going to go ahead and say the hypotenuse is 1 here, which means that if I have my hypotenuse is 1, if I want sine theta to be x, well then the opposite side has to be x. Notice x over 1 equals x, and that gives me that initial relationship that I pulled to begin with. So this side is going to be x. And now notice on this triangle, sine is opposite over hypotenuse. Sine of the angle is x over 1, giving me x, making this relationship true. This is just a way to visualize this relationship. So that actually helps me right here. Again, I can write this as arc sine of x. And now I can write sine of theta as x. That was something I knew already. But now I need to think about how can I rewrite cosine of theta based on this relationship here. So if we again look at our SOHCAHTOA part, I know that the cosine of the angle is the adjacent side over the hypotenuse. And let's see, I have adjacent, well, let's see, the hypotenuse is 1, that I know. The adjacent side, I don't know that yet, do I? Let's go ahead and call it A for right now. And I can find this side length based on knowing these side lengths. And what I mean by that is basically the Pythagorean theorem. If I use the Pythagorean theorem, I have a squared plus x squared equals the hypotenuse squared, which is 1. And I'm trying to solve for a here, so I'm going to subtract the x squared to the other side. And then I can square root both sides here. A equals the square root 1 minus x squared. So that's what goes here, root 1 minus x squared. Let me go ahead and write it up here too. So again, if you have a right triangle where one side length is x and the other hypotenuse is 1, the adjacent side will always be the square root of 1 minus this side squared, based on the Pythagorean theorem. So this divided by 1 is just root 1 minus x squared, and that's what I'm going to replace this cosine with. Okay, so finally we can get our answer here, arc sine x plus x root 1 minus x squared plus my constant. I think you'd agree that this is slightly easier to look at and compute than this one is. Here, if I wanted to plug something in, I'd have to take the arc sine, double it, and then take the sine of it. It's just slightly more work. Now, before I move on, I want to go ahead and check and make sure that this gives me the same result from what I did in this part here, when I changed the bounds for theta. So now I'm back in terms of x, so I can write it as integral 0 to 1 root 1 minus x squared equals, so here's my antiderivative, don't need the plus c because I'm going to evaluate from. Now here I can do 0 to 1 because I have written it back in terms of x. So now I'm going to evaluate. I get arc sine of 1 plus 1 times, let's see, that would be 1 minus 1, so 0, minus arc sine of 0 minus 0 times 1, so, okay. So let's see, I get 1/2 arc sine of 1, that's saying when the y-coordinate is 1, what is the angle? So we can think about on our unit circle here, when the y-coordinate is 1, my angle is pi over 2. So this is pi over 2, plus 0 minus 0 minus 0. And notice we get the same result as what we had gotten before. Our area is pi over 4. Okay, I know, that took a while, didn't it? So these aren't necessarily easy, but this technique does help us to integrate things like this. Now, if I wanted to generalize it even more, if I was taking the integral of square root a squared minus x squared, for example, okay, so if I was going to integrate this, I could use a very similar technique. Now notice in my helpful trig identities, again, we started with our Pythagorean identity. Now notice this one that I wrote here, which might seem somewhat obvious. I can multiply, because this is an equation and it's an identity, I can multiply through by a number. In this case, my number is a squared. And that will help me more with things like this. So if I were to rewrite this more here, so again, I'll write it here. A squared sine squared theta, a squared cosine squared theta equals a squared. So I can also write this as, if I subtract the sine to the other side, a squared minus a squared sine squared theta. So notice if I were to take this is similar to what I have here. I have a squared minus something squared. Now, to get a better idea of what that something is, I can think of it as being written as a sine theta all squared. So in a situation like this, what I would want to do is I would want to let x equal a sine theta. Now notice that was the case with what we did earlier when we had root 1 minus x squared. This is like 1 squared. So in our previous case, really a was 1, and notice I did let x equal 1 sine theta, or just x equals sine theta. So this is helpful for thinking about it in general. So in general, if a square root a squared minus x squared is involved, let x equal a sine theta, okay? Now, that's just a general case. There might be some situations, for example, like if I had the integral of root, I don't know, let's say 9 minus x squared, something like this. Okay, so if I had the integral of x over root 9 minus x squared. Now, I just want you to think about other techniques that we might be able to use for this one. Well, I do see an a squared. In this case, a is like 3, right? And that's not to say you can't use this trig substitution idea. You absolutely could. But notice with this one, I could actually use u substitution instead. I get 9 minus x squared. Du would be negative 2x dx. Here's my x dx. So that's when it's important to kind of run through this process of what can I use? Do I already know the antiderivative? Can I use u sub? Start with the things that are easiest first and then go from there. So I think that's probably a good amount of examples. I think I'll make another video that has more examples.